Yeah, I did that last time and I can highly recommend it. If you have the time, definitely go for it. It'll be fun. I think that's it. That's all the announcement. And yeah, thanks again for coming. Handing it over to Mike.
Okay, I'm all wired up, ready to go. So thanks to Praneeth and Yao Dong, who's here somewhere. Yes, these are our organizers. And thanks to MBZUAI for hosting this again. Last year was really a wonderful meeting. I had a great chance to get to know a lot of people and have a community. So I normally don't like to give the first talk. First of all, you have to bring up my slides, someone. There we go. Oops. Wait a minute. This is the wrong set of slides. Hang on. How did that happen? Maybe I gave you the wrong set.
We need to change that. It's fine, it's fine.
Yeah. Let's take a couple of minutes. Just use my laptop because I think I don't know how I did that. Anyway. Yes, exactly. I have an HDMI, so that should be easy. Here, let me take my glasses.
I think we can do it from screen just now.
I'm not sure what the heck I did here. All right, so Praneeth, could we have a adjustment here, actually? So I think what happened is I didn't save a bunch of edits I made on the side. Could we take the second speaker first?
Yeah.
Is that Eric? Eric, do you mind? All right, wonderful. Okay, I'm going to give you this thing on my head.
Guys, can you please unplug my...
Okay, good.
Okay. Oomph. I'm super amplified. I have to be careful. Thanks, Michael, for the nice introduction. It's a bit complicated, but so okay. Today I will speak about work that I've done mostly with a PhD student of mine. So he's called Louis Lecomte. So he's working at Lagrange Center of in Mathematics and Computer Science. So it's a kind of lab which is founded by Huawei in France. Mathieu Jonker. So Mathieu Jonker is a very old friend of mine. So he's more somewhere in. So you don't know him, of course, but he's not young. He's doing some queuing theory, and you will understand why there are some queuing problems there. And myself. Okay. And thanks, Praneeth, for invitation. I am very long in general, so I never speak quarter of an hour. It's like I am an old leftist from France, so I speak and speak and speak. It's like. Okay, so what is the problem? I will start with problem formulations, and I will try to speak a little bit about related works, or not much. Then I will do some numerical analysis, and then I will conclude. Nothing very fancy. So the problems that we will address, I think most of us today. So it's good to have the first slide on that. So it's about federated learning. So I look at the most simplest case of federated learning. I do a lot, especially in EIU. I do a lot of work on federated reinforcement learning, but I will not speak about federated reinforcement learning, despite I think it's a very, very nice direction to go. So in the classical federated learning, what you do, you are looking at the classical supervised machine learning paradigm, and so what you are looking at, you are trying to optimize the parameter x, okay, and this parameter x is the minimization of a function which is defined as a sum over n clients or devices. Each of these sum is a kind of a local loss function, so which is defined as follows. Nothing very fancy then. And you are trying to minimize the sum of this function, which is empirical loss. And there are many, many problems which can be formulated like this. So I'm looking at what I call lower non-convex optimizations. There are, of course, much finer results which can be obtained when the function f is convex, but I'm interested more in non-convex optimization. I will not derive super precise bond. I will left Emmerich to introduce you to a more when you are looking at the convex function. Of course, the results can be made much more precise. Okay, so what is asynchronous? So the classical technique to work with this type of problem is to work with as a synchronous distributed gradient descent problem. So what you do, so you have data sets, D1, Dn, so you have n clients, and you have a central server there. So the central server has a current model, which is denoted by xt. Then this model is dispatched to all the clients, okay, so which receives these parameters. They feed this parameter into their models, which is a nice multi-layer perceptron here, or I don't know, so perhaps it's a multi-layer perceptron. And so they have their local data, and they start to iterate. They compute a gradient, or it can be also, of course, a mini-batch gradient. If you are doing SGD, it would be more likely to be a mini-batch gradient. And then what you do, then you just back up this gradient to the central server, and then the central server updates the parameter, so define updated models with some step size, which is denoted gamma there, and it will be denoted eta later on, okay? Why? Because I've stolen these slides from one of my interns, Rustem Islamov, so we don't use exactly the same notation. So Rustem was more an intern of Emmerich, so he was a PhD track with Emmerich. He has been stolen by Switzerland, recently. Okay, so now what is that synchronous model? So which means that all the communication are synchronized, and so in general setup, the problem is that you have to wait for the server waits for the slowest worker, so which make problem, especially if you are in kind of cross device settings, or where you have a lot of users, and perhaps you will have some users are very, very slow to answer. So then you have many, many ways to define what is an asynchronous distributed gradient descent. There are many works. I will just describe some of this work later on in the literature survey, but there are many works. I will define the problem, and I will just present the algorithm I was looking at. And it works as follows. So now I start from time 0. So at time 0, I have also a central server, which is, I don't have a pointer there. Sure, but I should. So at time 0, you have a model, which is x0. So this model parameter is sent to all users. Okay, so these parameters are fed to the users, like this neural nets, and then they start to compute. But the thing is that you start to compute, but they don't compute at the same speed. Okay, They don't compute at the same speed, so they all start the computation of the gradient or stochastic gradient. And what happened is that, the first which has completed his work is client 1. Client 1 was the fastest, so he finishes to work faster, so he can send back his gradient estimate to the central server. Okay? And what the central server do is that is updating the parameter, okay, but without waiting, if you wish, that the other answers. In such case, you are not stalled by, you are not in the process of waiting for the other users to answer. So you update, and you have a new parameter x1, okay, which is updated according to this one central server. Then, and all the differences of the algorithm from here, so the central server decide to send this model to another user, okay? So here he repick user 1, okay, but it's not, so if you do that deterministically, it's not a good idea, so it will be bad. It's easy to understand. If you have very, very fast user, he will finish very quickly, then and will answer, so he will answer more soon. So you don't have to do that. You will have, so typically what you have to do is that you have to resend, in fact, with certain probability, I will discuss that later, you resend the job to other users, and of course, if a user is already active, he has to stack the job because he's in the process of computing one gradient, and he has to stack the job, and he will process the job later on, okay? So then the second user comes, okay? So the second user was still working with parameter x0, send back his update, but the update now is x1. Nevertheless, you get an update there, so you make it x2, okay? You update with a gradient update, and you update with a delayed gradient because, of course, the gradient which is here is not, you update according to a gradient which is delayed because you already have updated the gradient with the first user, okay? So there is some kind of delay which occurs in the asynchronicity and which makes the analysis of this algorithm a little bit more tricky than the classical analysis of synchronous algorithm, okay? So that the delayed gradient, and which makes all this difference. And the delay, as I said, may come from the fact that some of the job has been stacked. So because I did not show a queue there, but there is a queue which is building, because when you will resend, when the central server will decide to resend the computation, perhaps one of the users was already computing a gradient, so he has to stack. So there is a queue which is building up, a queue of gradient to be computed. Okay, so that's the overall algorithm I was willing to analyze. And so the main message there is that the communication is asynchronous, and the server applied delayed gradient. So you solve one part of the problem, but you have to cope with asynchronicity. So this is a general asynchronous algorithm I will look at. So of course you can make it more general. So and we have somehow some more general analysis, but to keep the thing simple, I define it like this. So you at a given iteration, so what you will do, so you ask at a given iteration, so you look at what is k here. It's not a time. This is why I don't use, because when you look at a synchronous algorithm, you have to define what are you looking at. So are you looking at time, okay, or are you looking at iteration of server steps, okay? So I'm looking today. I can look at time. Also, I have some results linked with time. But here I look at time measured in terms of number of iteration of central server, okay, which is something different. So k is iterate of the central server, okay, and what I do here, so at iteration k, there is one of the client or worker which is finishing his job. This job is called gk, so it's a random variable, of course. It's a server which is finishing his job. Okay, G of gk is stochastic gradient estimate. Okay, and of course it corresponds to the parameter which is used by user gk is ik, because it's a kind of parameter which is taken from the past. Okay, ik is less than k because we are not synchronous, and k minus ik, which is denoted here, is in fact it's a delay by which we are applying the gradient. Okay? And what we do next is that we update the current model. We update the current model according to this formula, so xk plus 1, so it's g of gk xik. And what I'm taking into account is the probability, so it will be important in my talk. So if there is a probability, the only thing that we do is that we reallocate the job for the user with a certain probability. So it's a very simple policy, but it's compared to classical asynchronous gradient algorithm, we use a non-uniform policy. So we reallocate the job to different users with a certain probability, okay, which are not uniform, and I'm taking that into account by dividing the update step by this probability P of the user GK. Okay? And then what the server does, it just assigns the new work KK plus 1 to compute the new asymptotic, the new stochastic gradient, which will be GKK plus 1 of xk plus 1. That will be used to update. So I could generalize that a little bit. I could have had a delay there if I would like to analyze a strategy which are good strategy like fedbuff, for example, where the server did not necessarily update immediately the parameter. I have 10 minutes left. No,
10 minutes done.
Done. No? I did not start. Okay. Okay. So you could imagine to have something a little bit more complicated there by adding some delay, because you can buffer. You can make a buffer of updates. Okay. So you can buffer the update and decide to update the parameter after. For example, if you have received, say, B updates, then you update. Okay. Sometimes it's better to do that, but I did not do this analysis there. Okay. So of course the clients IK which are returning to the central servers comes in natural order. Okay. They are not controlled by the server. It's like they just return to the server because they are finished to do their job. Okay. But the server decides how to set, in fact, the next users that will process the next gradient. So there is a strategy, and this is a very simple strategy. So I think in the future we are imagining the way what we will do is that we will look at the status of the queues. Okay, so I think we will have a routing strategy. You can have smarter routing strategy. Here it's a random pooling, so we pool randomly but with non-uniform pattern. Okay, but of course we don't take into account that some user, for example, might have a lot of gradient to compute. And we did not take that into account yet. Okay, so related work. So I will go fast, especially because there are a lot of experts in the rooms, which are much more experts than me. I see Gorbunov, I see Sam Horvath, so I will not be. So look at this. A lot of work which has been done since French guy, Baudet, which was the first to analyze this type of stuff. I was 15 years old, long time ago. I don't know Baudet, but Bert Sekas did the first analysis, asymptotic analysis of synchronous gradient. There are a lot of work which has been done by you, Pranit, with fixed delayed, Arjevani. So there are a lot of work done by the EPFL team with Koloskova, Mishenko, but they, to me, in fact, so I started by looking at this work at Koloskova, and I think there is something that can be improved. I will explain. So because they all assume some kind of maximal delay, okay? And maximal delay gives you bounds which are extremely pessimistic, okay? There is a kind of maximal delay because you have, if you look at the dynamic of the system, at the beginning of at the initialization, you start C jobs, okay? And the number of jobs in the system is always C, so you have always C clients which are working, okay? And the maximal delay can be computed like that. Okay. So our theoretical analysis is done as follows. So we use very, very classical set of assumptions. Lipschitz functions. So we use unbiased estimator of the gradients with bounded variance. So we take bounded variance there, so we can use more better assumptions, of course. We have also the classical heterogeneity assumption. I think it's a G square because it's an old version of the slide, so G square later on in my slide. So it measures the heterogeneity of the gradient, and we have also some locality. And then the quantity which is important there is MIKT, okay, T being the last time index. So MIKT, in fact, it's a bit, yeah, it looks a bit strange, but in fact, in words, it means what? It means that if that is a number of CS step, okay, of central server steps that need to be elapsed when you send the gradient to client I, okay, and this will be the time to wait until the gradient will be processed, okay. So xik, there are the length of the queue, so the number of tasks on the client I which has not been processed, and GL are the index of the clients which are currently released, okay. And that's a quantity which is really of interest, and the quantity which is very important in all the analysis is this MKT. So MKT is the sum of the expectation of this quantity. So it is related, so the quantity which is very important in our bound is, in fact, what is the average time, what is the average number of time step that will be elapsed when I send the gradient to client I until, in fact, the gradient will be processed, okay? And that, the analysis is not different from the analysis by Koloskova or many, many other authors in the sense that we have a kind of virtual iterate, so there is nothing very, very fancy there, okay? I'm finished already. And there is nothing very fancy there, but the thing which is important is really that so we express all these bounds in terms of this kind of expectation. Okay, so our bounds, in fact, are much, much better than the others. No surprise, okay? We have that's our efficiency factor, so it's more than 100 somehow, so depends in the configuration. And this is because we take a kind of very simple scenario with 100 nodes. We have 10 fast clients, 90% of, and then what we call μF, in fact, is different speed between we have two groups of clients, 10 fast, 90% slow, okay, 10% fast, and μF is in fact it's a ratio of speed between the fast and the slow, okay. And of course, the analysis of Koloskova is really bad because, or even FUDBUF, because they are penalized by the fact the way that you have this tau max, which is very large in their case, and which is doesn't need to be large. Okay, so, and now how it is related to, and I finished Pranit, I promised, how it is related to Jackson networks. In fact, it's a closed, in terms of queuing system, it's a closed Jackson network. So which means that you have a central server, okay, and you have queues, okay? The number of works in this net is always C, so you only have C. So you send C process, and you will always have C gradients which are computing right now. So which means that the C delayed gradients. So maybe they are in queues, okay, or they are currently processed, but you have only C gradient to process. So you have, it means that you have a C jobs in the network, and the number of jobs in the network, which is called sometimes the concurrency, is fixed during all iterations. And what you can prove is that there are a lot of work. I will not have time to explain, but there is a lot of work on these closed Jackson networks. You have, for example, you can define what is the dynamics of the queuing system. So how many at time t, and now t is really time. It's not like iteration time. Okay, it's t is really time. At time t, what is the number of clients in each of the adjoint queues? Okay, so that you can define it. It's a Markov process, assuming that you have, in this case, I assume that I have exponential, it's Poisson process, which means I assume that each work takes a kind of independent exponential time, because it's much easier. I could have general processing time, even random processing time, even deterministic processing time is doable, but it's much more complicated because then you have to define what is called the edge process, which is more complicated, but it's very, very simple in the scenario where you assume that each job takes a kind of exponential time to be processed. So it's, and then you processing time. So μg is the intensity of this of the jump process for each client, and pi are this the probability of setting choosing the client I. Okay, and you see that the distribution of the Q depends on theta I, which is the ratio of pi over mu I. You can also obtain a kind of expression for asymptotic expression, at least for the delay, according to what is called the Palm probability there. So EC minus 1 is the Palm probability. So you have an explicit expression for this average delay. And so it's a bit difficult to explain what is a Palm probability here, but it's a classical method in queuing theory, at least. And of course, what we have done also is that we can have a very explicit expression of this MIKT in what is called the heavy traffic regime. So heavy traffic regime means that most of the time all the queues are full. Okay, so which means that all the time, otherwise it's very, very complicated. So it's because there is something to understand just if you are a bit in queuing system, is that if all the queues are full, because we have Poisson, you have Poisson variable, the delay is very easy to compute, because it's like it's always because of the memoryless, the exponential distribution are memoryless. In fact, it's always the time at which you will observe a point is really like distributed according to. It's always distributed according to an exponential. It's an exponential time with the intensity, which is the sum of intensity of the Poisson process. So that's so a lot of things can be done. So we can interpret most of these patterns. This is done in our work. We did not put that on archive, so it's very fresh. It has been submitted to ISTAT, but we did not release it on ISTAT. But I can share if you wish the current version. It's not. Yes. Give me 1 week to really clean all these things. But we can using this. Heavy traffic asymptotic, we can retrieve, in fact, at least in some cases, we can retrieve the part. And the thing which is very important is that you gain a lot. You see that, I think, there. I'm not sure I've included this, because I did that. I was taken by time yesterday night. Michael was calling me to restaurant, and so I did not have time to finish. But you will see. He said, Rick, you should come. So we have a wonderful meal. So this is why I put the slides. I was trying to finish. It's your fault. And so you can show there that, in fact, it's the use of non-uniform pattern is very important. The fact that you use PI, which has not uniform, if you want to have a large gain, in fact, you need to use non-uniform probability of a signing job. Okay. That's very important. Okay, so it's not, and the way it should work, it's a bit intuitive in the sense that you should. It's a bit counterintuitive when you think, is that you should assign job more frequently to slow users, contrary to what people believe. And I will explain to you. It will be a quiz. Why? In fact, intuitively, you say, okay, so you should not pull more often fast users. You should pull more often slow users. Okay, thanks a lot. So I will, if you are interested, I can share the current version. It's not perfect, but it's there. And yes, ready for question.
Yeah, while Mike's setting up, maybe there's a quick question for Eric. If there isn't, I can ask one. What do you think? How do you think lower bounds would work in this kind of a setup? Like, so, what would be like the tightest lower bound we could hope for?
I think it's difficult. So there are many things which remain to be done. So we don't use control variate there. So it's like very, very brutal stuff. So I think I don't know. But I think we are very far from. So we just noticed that in fact, the message is that the way people, so we did not really change the analysis. It's more like the way people upper bound, in fact, what is called, I would say, the variance of the gradient, and because to take into account the fact that the gradients are not updated at a regular scale, is very, very brutal and very pessimistic. Okay, so which means that you can do much better. And the second message is that assigning non-uniformly users is a good idea, and it's really linked with, you can optimize somehow the way when you know the speed of each user, and it's a bit surprising. The way you should do it is a bit surprising. Yeah, it's not completely intuitive.
Thanks, Eric.
Thanks. Back, it's your turn. So, be careful.
I realized I didn't really introduce Eric, but I guess everyone knows Eric. So you don't mind. And I don't need to introduce Mike either, so yeah, I'm just going to let him speak.
Would it be the right slate of slides?
It's okay. We'll just leave it from here. And just plug it. I'll check from there. Just plug the
Okay. Okay.
Guys, can we have this slide?
Okay, as I was saying, I don't like to give the first talk, so boy, I feel much better. Okay, so I think I'd like to complement what Eric was talking about. So Eric was talking about kind of in the engine room of federated learning. I want to kind of think about the conceptual level. Why are we doing this? You know, what is the point of all of this? So here's a usual picture I probably stole from one of you. So this topic is being cast within the overall rubric of AI, intelligent systems. And one way to think about that agenda, which is the one that seems what everybody talks about, is creating this entity which is intelligent, mimicking human level intelligence. I don't want to get into a long discussion of that now, but I don't like that framing. I don't see the point of that, taking out a human and putting in a computer. I don't really see the point in that. I think what's much more interesting is realizing that when you put collectives together of humans, really amazing things happen. Markets happen, art happens, culture happens. When you put together human collectives with computers all mixed in, brand new things are going to happen. And to me, that's really what's exciting. Okay? And so now you have to take an economics point of view, say the intelligence isn't in the individual. Yeah, they need a minimal amount of intelligence to make the whole market really work. The intelligence is in the collective. And anyone who does economics will tell you that. The market is intelligent. It responds, it adapts, it's robust, it works at various scales. It has its own algorithms, which are not the usual ones we put, or not necessarily gradient descent algorithms. Okay, so anyway, I could go on about that, but I won't here. So in that view, federated learning is just about trying to collect a lot of data from a lot of people, okay? And maybe give them some guarantees and all, but really you don't care about the people at all. You care about Google, who's trying to grab a lot of people's data and then use it for their own purposes. And you're trying to build bigger models. Where do you get the data from? Well, you just grab it out there. So that's federated learning. An alternative is to say, no, we're trying to build these collectives. It's all about the people. Okay, the central thing is just kind of there to manage the thing. So it's all about these agents and empowering them and trusting them and giving them, access to not just how their data is valued, and it's also then about supporting the overall collective effort, which will do things that no one individual could do or no central entity could do. Okay, so hopefully you agree there's some value in thinking this way. I think it's actually a far more interesting thing to think about. And so now you have all kinds of problems that come up. Here's four I'm going to kind of allude to in this talk, but there's just tons. There's the usual federated learning kind of things about compression and gradients and all that. But there's all kinds of other more economics ones. Like how do you manage information asymmetries? The information is spread all over the place, and one person knows more about something than someone else knows. But that doesn't mean they're necessarily the leader. They may be the follower. It's how do you manage it, and you don't want to just transfer the data to somebody. You want to you have competitive advantage to holding your data, so you want to respect that. Uncertainty, we don't talk enough about uncertainty in machine learning these days, to my view, and that's a whole separate talk I would give. But how do you manage it in these collectives? How do you deal with all the biases, and then how do you incentivize? So if you don't put the word incentivize in there, you're not really doing full economics. Praneeth and I have been working on this, and he'll talk more about incentives later. Okay, so let me just jump in and give you an example of incentives meets machine learning. So this is a work with Stephen, Michael, and Jake at Berkeley. And so let me just say a couple of words about the theory of incentives. There's a book with that title, written by a French person, Lafont. And so roughly speaking, let's just start with game theory. You all know what game theory is. Game theory is not really the engineering field. Game theory is more of a science field. It's trying to predict behavior by making a model, running the model, putting players in a game and seeing the outcomes, and say those outcomes correspond to what I see in reality. Just like a physicist who writes down some equations, runs the equations, looks at reality, says, oh, it's a good model because it matches reality. That's what game theory is doing. Okay? And now there's different kinds of games. There's symmetric games, there's asymmetric games, there's collaborative, and they try to explain different things in the real world. Okay? Now, an engineering mindset takes that in physics, and they say, we're going to do something called mechanical engineering, which is to invert the equations. We want a desired outcome. The bridge stands up. What are the principles that will give us that? In game theory, the inverse problem is called mechanism design. And there's different, for each kind of different game, there's a different kind of mechanism that arises. Most of the work you will read about in game theory and mechanism design is about auctions and about symmetric games. So if the game is symmetric, meaning all the players, there's no real distinction of a leader or a follower, they all come in. They may not know things about each other, so they have to average and all. Those are called Nash equilibria. The game concept is a Nash equilibrium. It's all symmetric, right? The corresponding mechanism for a Nash equilibrium is an auction. And then there's all kinds of different auctions, right? But auctions are about players who are symmetric. I think in our world, it's much more common to have asymmetries. Okay, you come in and someone knows more about something than someone else, and everyone recognizes that. That's an asymmetry. All right, so in the game theory world, asymmetries are called Stackelberg games, and you have Stackelberg equilibria, and there's a whole field there. But now what's the mechanism that is the inverse of a Stackelberg equilibrium? That's called contract theory. Okay, so hopefully that helps place everybody. So if you want to work on mechanism design with asymmetries, that's exactly contract theory. So you all know a little bit about what contract theory is. It's that you have these agents, and a principal wants to get them to do something or to buy something or whatever, but they know things the principal doesn't know. They have some skill, and so the principal would like to get them to use that skill in some way. Or the principal wants to get them to buy something. So airplanes are the best example of this. It saved the airplane industry to start using contract theory in the 1980s. And what does that mean? Well, they invented the whole notion of different classes of service. So business class gives you a little bit more of a service, and you pay a lot more money. But there are people whose price point is such that they will go ahead and pay that, and then the airline reaps the benefit, and then there's a few seats filled at a high fare, and then lots of other seats are available for lower fares where people don't have the same price point. So the overall social utility is high. Everybody gets something they kind of want, and the airplane is full, so the revenue is high. And if you design it right, it kind of works over many years, and you tweak it and all that. And people, of course, hate the airlines because they do this. But in some sense, there would not be airlines if they didn't do this. Okay? All right. Now, this isn't, there's lots of other domains where you're trying to get like a boss wants to make a worker do something, and the worker knows something about their skill, so they're trying to get paid a certain amount. And there's this asymmetry. Okay. So anyway, the theory is really quite vast. But what's interesting, there's almost no statistics in it. There's no statistics. There's no learning. These agents aren't learning anything. Some designer, like the airplane, sat down and designed some things with some crossing curves and some equilibria concepts. All right, but then you put it out in the real world and hope it works. If it doesn't work, you tweak it a little bit. So that's a huge opportunity for people like us. How do we think about asymmetry of information and learning systems? All right, so here's a real-world concrete example that has driven some of our thinking in this. You all know what clinical trials are. They cost tens of millions of dollars each year to run. It's an asymmetry of information situation. It's not thought of that way. The FDA in the United States thinks of themselves as a statistician. They're testing hypotheses, and they're trying to make sure false positives and false negatives are managed. Okay? The problem is that the hypotheses aren't just coming out of a scientific theory or just out of the air or something. They're coming from self-interested agents, the pharmaceutical companies. All right, so you're not just testing random hypotheses. All right, so these numbers reflect partially that uncertainty. So let's dig in a little bit more. The principal is the FDA. So this language is, you say in stack overflow games, you say follower and leader and follower. And when you do the inverse thing and you do contract theory, you call it principal and agent. That's just language. All right, so the principal is the FDA. They only have partial knowledge because they're trying, here's a new drug candidate. It's some protein that's been altered in some way. And the FDA doesn't know anything about that protein, really. But the pharmaceutical company knows a lot about that protein. They've been studying it for years. They've tried it out and all that. And plus, they've done maybe some internal testing and so on. The FDA would just like to ask this agent, tell me how good your protein is. The agent is not motivated to tell for competitive reasons, and also they want to get good licensing terms and so on and so forth. So they won't. They will lie. Okay? And this happens all the time. People lie for all kinds of good reasons. It's part of how humans are. Okay, so how does the FDA actually think about this problem? Well, I will argue they don't think about it the right way. They think about it too much like a statistician or a machine learner. So they think, okay, the world has, let's suppose, good drugs and bad drugs. Bad drug doesn't mean it hurts anybody. They screen for that. But bad drug means it's just not effective, doesn't do anything. Good drug means it really changes things. It makes things better. All right, and they set it up so that if it is a bad drug, the probability of approval is like 0.05 or less. That's the false positive rate. And if it's actually a good drug, the probability of approval is 0.8. That's the power. And they're really good at this. They're really good at the statistics. Is this a good protocol? Well, it's optimal. It's the Neyman Pearson test. You can't beat it. All right, but it's not a good protocol from a game theoretic point of view. So in case one, let's imagine small profit to be made. So 20 million to run the trial, that's the numbers you saw. And if you're approved, maybe you make 200 million. It's a small niche drug. Okay, so the CEO looks at that numbers, all these numbers, and does a little calculation. The expected value of the profit, if counterfactually the drug is actually not effective. No one knows that. The CEO doesn't know that, the FDA doesn't know. But if counterfactually, let's just imagine for a moment, do the thought experiment, it's not effective, then I will on average make minus $10 million. All right, so the CEO looks at that number and she says, okay, engineers inside my company, only send in drugs that are really, you're pretty convinced are effective. Otherwise, we're going to be losing money. So in that moment, the incentives are aligned and the FDA gets mostly good candidates. And when they do their Neyman Pearson testing, good candidates go on the market, everything is happy. The real world is more like this thing on the right. It costs $20 million to run the trial. And if you're approved, you might make $2 billion for the first year. That's more like ibuprofen or lots of more other drugs. And now the CEO does the same calculation. She finds the expected profit, if my drug counterfactually were not effective, is going to be 80 million. And so now she goes back to the engineers inside the company and says, send in everything you've got. Okay? Flood the FDA with all the possible candidates. So why are they doing that? Well, because of that 0.05. And it's actually like 0.001, but anyway, that number is big enough that if you send lots and lots of candidates, some of them will squeak through as false positives. They will go on the market, and your expected profit is huge. And so you do that. And people, these drug companies absolutely do this. So lots of drugs on the market are, in fact, if you retest them later, they're not effective because of this. Now, is that bad? Yeah, that kills lots of people because people could have had a better alternative, and they were taking something that wasn't actually helping them. So the market eventually corrects and so on. The FDA starts to get a reputation and so on, but this is not good. All right, so how do you fix this? So long story short, we've developed a theory. We call it statistical contract theory. It's just getting going. This is brand new. And just roughly, here's a contract. So what is a contract? It's like the business class. In general, a contract is an option and a price. Option price, okay? Business class, economy class. So here, the options will be things like different licensing terms you might have, okay? Where you can do it, how much you can do it, how long, and so on. And then, the price to enter into the clinical trial. Okay, so agent will be given this option, this protocol, and the agent can either opt out and say, forget it, I walk away, I'm not going to try it with this particular candidate, or they can say, okay, I'm in, I pay a reservation price R, like 20 million, then they're going to choose a payout function from a menu, and here's where the machine learning comes in. What payout functions do we use? What payout functions do we use? Well, we're going to design that, okay? We're going to choose those. And that's going to be where all the interest is. And now the new component here is that in classical contract there was no data gathering. Here there's data gathering. You gather a random variable z, which is the clinical trial, which is drawn from the true distribution out in nature. No one knows theta, but nature does. So you draw from nature. All right, and now you get the payouts. Agent receives a payout, which is F, the thing they chose, applied to that, and the FDA gets a utility. They have to pay out that amount, so they pay that, and then theta as well. It depends, because they will get reputation if they approve good drugs mostly. So our problem as designers is to design this menu. So what kind of menus are reasonable? Well, first of all, you have to write down a notion of incentive alignment. If you don't write that down, you're not doing economics or mechanism design. And so here it's pretty interesting and straightforward. The incentive alignment is the expectation under the null hypothesis, right, of how much it'll cost you minus the reservation price. Okay? So you want that to be negative. This is the agent's expected profit. If that were positive, the agent would have expected profit, which is positive. That would not be good. So we got to make sure that this holds. And it really is only under the null hypothesis that it matters. All right, and so now we can prove a theorem. And it's right here at the bottom of the page. We can prove that a contract is incentive aligned if and only if, it's the only if which is key here, all payoff functions are E values. So I'm up to 50. Oh, you're going in the opposite direction. Oh, usually it's a count down. Okay, all right. All right, so yeah, fine. I'm going to finish up here pretty quickly. Okay, so what is an E value? Well, E value is a measure of evidence in statistics. Okay, you all know what P values are. They're kind of bad measures of evidence from last generation. E values are better. An E value is an expectation under the null hypothesis of a non-negative random variable being less than or equal to 1. If X satisfies that, it's called an E value. More generally, these are non-negative super martingales. And so you should think about it like a p-value is the probability on the null hypothesis being on the tail. If that's a small number, that's evidence against the null hypothesis. Okay? Here, under the null hypothesis, it's an expectation, not a tail probability, that's less than or equal to 1. Okay? So if it's less than or equal to 1, that's kind of evidence, it's not evidence against the null hypothesis. But if it's a big number, that's evidence against the null. All right, so it's just a different way of kind of thinking about null hypothesis testing, but it's much better because martingales, you can have stopping theorems, p-values don't. You can put martingales together, p-values you can't, and so on. Anyway, that's the statistics side, but what we've shown here is if and only if. That if you're going to design statistical contracts, you should only use the world of non-negative super martingales. All right, so that now tells you as a machine learning person, this is the objects we have to learn and we work with in our learning protocol. Okay? Okay, so long story short, we've been doing that in several follow-up papers. Since I only have 15 minutes, I'm going to stop here and not tell you about those follow-up papers. But we have some papers where you incentivize in the federated learning setting agents to provide data. You ask agents to provide more data. It has a cost. Statistical contract theory will apply there. And again, I think a couple of the other people in the audience will follow up a little bit on that. That's all I want to say. So I had a second part of the talk. Let me skip that. Let me just advertise this one. I'm not going to get into it. But this is a paper that appeared in Science 2 weeks ago, and we're pretty proud of it. It's also about uncertainty and different, two agents. But here, one of the agents is AlphaFold, okay? And AlphaFold provides biased data, and the other agent is someone who wants to use AlphaFold to do science, okay? AlphaFold generates lots and lots of data, but some of it's bad for especially the scientific hypotheses you're interested in. Okay, so let me just show you an example real quick before I go. Here's some pictures of AlphaFold. Here's the scientist in the lab, and here's AlphaFold. AlphaFold can do hundreds of millions of sequences. Scientists can only, up to date, only have hundreds of thousands. So if you start using AlphaFold to do hypothesis testing, here's an example of a hypothesis test. You can go from 10,000 data points to huge numbers. And let me show you a picture that'll convey the issue. Right, so here is an AlphaFold prediction, and here's the actual truth. AlphaFold's quite bad here, but it's good overall. The accuracy is overall high, but it's bad here. Why? Well, this is a situation of these strands of intrinsic disorder that AlphaFold doesn't have a lot of training data on, but this is exactly what the scientists are interested in. This is on the edge of knowledge, and that's often going to be the case. If you want to be on the edge of knowledge, there's not a lot of past data, and AlphaFold will make a lot of errors there, and so it's going to hurt you doing science, okay? And so now if you plug all the AlphaFold stuff into a hypothesis test for this particular thing, does intrinsic disorder have anything to do with protein viability, activity? Here's what happens. And so this slide I want to just spend 1 minute on, then I'll finish. This is a statistic here. It's an odds ratio. If the statistic is 1, there's no effect. If it's bigger than 1, there's an effect. So big deal, all right? If you use AlphaFold's output, here is the confidence interval you get. Small confidence interval. You have a huge amount of data from AlphaFold. So you get really high confidence, right? But we did a big Monte Carlo experiment on half of the AlphaFold output, and here's the actual truth. Yeah, this is not covering the truth at all. So it's wildly off. Even though the overall system is accurate, when you use it for hypothesis testing, it can be wildly off. If you say, forget AlphaFold, let's just use the ground truth data, you get this confidence interval. It's a classical statistical confidence interval. Unfortunately, it covers 1, and you can't make any conclusions. So we have this new approach called prediction-powered inference, which gets the best of both worlds. It's going to use the AlphaFold stuff, but it's going to correct the biases and allow you to do unbiased hypothesis testing. And we've done this in a whole bunch of domains, in computer vision problems, and other biological problems, in voting problems, and so on and so forth. And so I'm going to stop, but I'm not going to tell you how we do it. But if you want to come up to me, I'll tell you how we do it. It's sort of a new statistical idea. It's not completely new, but it's a new statistical hypothesis testing idea. Okay, so anyway, that part of the talk I didn't give much detail, but again, it's about an asymmetry. It's about some knowledge or some object over there that someone designed, which has some purportedly some knowledge, and there's you wanted to use that, and there's this asymmetry. How do you manage that? That's my big issue. All right, thank you.
Any quick questions while Samuel sets up? So maybe I can ask a question. How do you think these ideas would work if the knowledge needed to make a decision is sort of distributed? So in the talk, you were the agent was the manufacturer, the pharmacy company. There was just one company which knew all the right information. What if this information is distributed across multiple people?
I mean, the contract theory is about distributed asymmetries, right? So I think it arose, there was general equilibrium theory, which is about producers and suppliers and finding a price, and then now you know the quantities that everyone should go for. But now if you go inside of an actual company, you've got managers and you've got workers, and the manager says, oh, the economic theorist told us our target should be X. How do you actually execute? You can't just tell people to produce X. You have to incentivize them. So it was about that. So there were multiple managers and there's multiple agents, and there can be asymmetries in both directions. I'm particularly interested right now in a problem where you have a hierarchy. So I'm a principal to some agent. I'm trying to get Alain to do something, but I'm also a agent to some principal. Eric is trying to get me to do something. All right, and how do I behave when I'm both a principal and an agent? That starts to get into really interesting architectural questions, and those are not been asked in classical contract theory. There's lots and lots of things. It's not hard to think of them where you get into all these asymmetries. And I don't think contract theory answered, but a small sliver of them, because they were focused on a certain set of problems, save the airlines. But just this mindset to me has been very, very helpful in kind of liberating me from classical machine learning thinking.
Thanks so much, Mike. MS and PhD in statistics at KAUST, advised by Peter Richterich. So he's broadly interested in federated learning, distributed optimization, and efficient deep learning.
All right. Thank you, Pranit. So what I want to discuss today is, So what I want to discuss today is the personalized federated learning, and in particular, what we're going to look at is how to kind of remove one of the more serious issues within federated learning, or when you want to train your model in distributed setup, which is data heterogeneity. So this is a joint work with Konstantin Mishenko, Rustem Islamov, and Eduard Gorbunov. Konstantin is in Samsung Research. Rustem is currently a PhD student in University of Basel, and Eduard is a postdoc with us, and also he's in the audience. All right, so let's just discuss the setup. So, as was already said, we consider a standard federated learning setup, whether that's the cross-silo federated learning, where we have different institutions. You can think about hospitals that want to collaborate in order to have, let's say, some intelligent agent to help you to do the diagnosis. But the thing is, they cannot directly share their data because this data might be private. Also, one of the things that we're also looking at is the cross-device federated learning, where now devices are some constrained devices, such as mobile phones, where we want to train some global model. That might be a recommendation model that we want to train on those devices, but also use it on them. So the deployment is also one of the challenge. As was already discussed, especially in Eric's talk, so the standard objective that we tend to optimize is we're just trying to find a global model that I'm going to denote X star, such that when we have local loss on each client, that this X star acts as a good approximation to the true minimizer for each local client. So there are certain limitations to the global model, in particular if we assume that there actually is data heterogeneity. So this might be often very restrictive, and in many cases it might not even exist. So think about this simple problem where you just want to do the next word prediction, where actually the next word's going to be underlying on the person or client that just wrote the first part of the sentence. So in order to kind of remedy this potential issues, a lot of work was done on fine-tuning and personalization, and in this talk I'll focus on the second part. So how the objective then changes when we have the personalization. So instead of trying to find one good global model, what we will try to do is we will try to find a good X star for each single client, such that that X star is as close as possible to the true minimizer for the client. But in order to benefit also from the personalization, we somehow have to link them together. One of the most popular approach might be meta-learning, and I guess some of you in the room already have some work on this. Also, another potential way that I will more focus on this talk is the partial personalization. So what's partial personalization is, we're going to have a split where we have part of the model that's going to be global, and then we have a part of the model that's going to be personalized and that's going to be unique to given client. And then what's our aim is we try to find such a good global model that when we personalize well, we're essentially going to resolve the local problem. And the motivation here is that if we get essentially the split right, then we should also generalize well and have essentially the benefit of collaboration comes from the theta star here. So standard ways how to achieve that. What we can do, for instance, we can personalize the input layer if we assume that there is a lot of heterogeneity that's coming from the input itself. Also, when there is a heterogeneity that comes from the output, we can also personalize the output layer. But also another, I think currently very popular approach is to include some adapters. So we would have some adapters that are local to each client that will personalize our model, and very common way to personalize model, especially for language models, might be LoRa adapter. Okay, so with this, this is general setup, and now comes the main contribution of our work. So when we look at this partial personalization framework, we wanted to see whether you can actually benefit from partial personalization. And how we think about that, we think about the partial personalization as some kind of overparameterization, and that's what led us to propose this over-personalization that I'm just going to present in this slide. So first, so kind of the motivation, what we have here is for machine learning, for general machine learning or centralized machine learning, we know that kind of over-parameterization can help us quite a bit. But the thing is, for instance, when we have a data heterogeneity in terms of, let's say, the prediction, so giving some input giving the input, the output of the model should differ across the client, that automatically limits you that you cannot achieve the over-personalization globally. So that automatically you cannot use the global model just like that, because it's not going to have a property that we can actually achieve zero loss. So how to go around that is what we call this over-personalization. So what you have here, we assume that what we have is split such good enough that what we can achieve is, okay. All right, so what we can achieve is that we have a global model. Then if we properly solve this local adaptation, then what we assume that there actually exists such global model that can exactly solve a local problem at each single client. And with that, what turns out are the great implications of this, that if you get the personalization right, then you can achieve zero training loss for each client. And also another thing is why we frame this as an assumption. This is actually kind of as general as over-parameterization, because you can always achieve that if you have a big model that has enough capacity. Then essentially, if I just say that every single parameter is local, then I'm going to achieve this one. Although, actually, like the problem in practice will be to find the right balance between the local and global models. This is not something that I'm going to discuss. This is something that we would like to approach as a future work. But what I'm going to show you is, like, once you have this nice property, that essentially it almost acts as an over-parameterization for federated learning. All right, so with this, once we have the notion of over-parameterization, we can also introduce this new objective that we're going to focus on. So our goal is to find such global parameter such that this operator equality can be zero, where this operator is defined as a gradient with respect to the first part of the split that we want that to be zero. And with this, essentially, what is this objective right here? So that objective, what we're trying to do is just we try to find a first-order stationary condition for this over-parameterized or over-personalized objective. How we're going to solve it is we're going to use the algorithm that we propose here that we call fine-tuning followed by global gradient, or FFGG. So what you can notice that the algorithm looks pretty much as the standard method that we would use for federated learning, where the difference is that what we're going to do first, we actually do not just take a single gradient step, but first we're going to solve the local subproblem, where the local subproblem is just to find a good local adapter considering our current iterate. Once we have that, we just evaluate a single gradient, and that's what we're going to use as our update. So with this, what you can notice here that this algorithm has a quite nice property. It's still stateless, so we can also deploy it for cross-device federated learning, and we're also going to show that if you do, so here, that you're actually like doing more and more of this local work, you're actually going to get a better convergence. So you're going to benefit from more and more local work, which is not always the case in federated learning due to the data heterogeneity. When we look at the theory, so this is what kind of brings us to the benefits of over-personalization. So if we just look at our convergence of this operator, so it goes to 0 OS as a deterministic algorithm, despite that we do the sampling of the clients. And the reason for that is that we have this over-personalization property that is essentially equivalent to over-parameterization in general machine learning. And what is the assumption that we make here? That we assume that this operator is co-coercive, which you can think about as a generalization of convexity and smoothness. So, and here, that's something that I hide here. So essentially how the convergence would look like if you don't do enough local steps. So you would have some term that you can only reduce with the extra number of local steps. But if you do enough local steps, then you can actually get just a deterministic convergence. So the nice implications of this ones are that once you have over-personalizations, there is no any notion of heterogeneity that's going to appear in the rate. Plus, what we also can show that once we have over-parameterization plus co-coercivity, then you can actually see the benefit of cooperation. So firstly, what I said is that the conditions that we solve are only like the first order stationary conditions of the original problem, but we can also show that if over-personalization and co-coercivity holds, then you actually solve the problem. Also, what you can see is that if you solve this problem, you actually solve the original problem. Therefore, if you have a new client that that just joined, what they can use, they can just start with the parameter theta as their good global model, and all they have to do is actually, they just have to fine-tune this W, which was the local parameter, in order to get the best performance. And let me just quickly finish with what was a part of my title, which was breaking the curse of heterogeneity. So how actually this, so it's essentially this over-personalization where we show that it does solve some of the kind of important issues with federated learning in general. So first of all, when we look at Byzantine robustness, which is a standard problem in federated learning, as federated learning is a collaboration among mutually untrusted clients, then this would be very easy target to poisoning because anybody can join. But the thing is, if you do personalization right, then we can show that you can actually run just standard Byzantine robust algorithm, and then what cannot happen is that your Byzantines would just simply hide in the noise. So actually for that, once you have over-personalization, you don't need momentum, you don't need any variance reduction, and you get the right benefits. The same goes for asynchronous learning that Eric was talking about. So now the thing is, if you get this all right, then we know that asynchronous SGD, well, in order to analyze it well and provide the proper convergence, we have to assume that the data are somehow homogeneous. If that's not the case, then theory is very complicated, and we cannot even guarantee the convergence to the exact solution. Once you have the over-parameterization, over-personalization, you just apply this algorithm that I just showed you, and you can converge to the arbitrary, for even arbitrary heterogeneous data if you do the personalization right. And let me quickly just show you the experiment. So first, it's just a simple quadratic that follows our theory, where we show actually that you benefit indeed from the local steps, and as you increase the local steps, you get better and better. And also when we try this on some real-world data set, that you can see that essentially if you do the adaptation right, then you get the state-of-the-art performance, and even with the comparing to the best model, you are either on par or significantly better due to the way how we construct the algorithm. All right, so let me just quickly go through the conclusion, where what we propose is the new kind of personalization framework, where we propose also the new algorithm that can be stateless. We can show that local steps probably help, and we can also handle the heterogeneous data, where this key was over-parameterization, then can help us to remove the effect of data heterogeneity. And still the key limitation, what stays is like how to do this well in practice and what's the right split of the parameters that we should use. All right, thank you. If you want to check the papers on archive.
Thanks so much, Sam. Any questions?
I have a stupid question. functions which are not gradient of convex functions. Do you know examples? Do you know example of co-coercive functions which are not gradient of convex function? Or?
So here, essentially, it's for us, it's not necessarily just it's not just a gradient because we assume this co-coercivity. I think. Okay, can I go back? Yeah. So we assume here so here we assume the co-coercivity with respect to this operator, like FM, but that FM actually, it's not only like the operator in the first one, but it also has this other term where we have to do the proper personalization. So it's not directly like just a gradient, but yeah, but going back to your question, I do not know any examples. But maybe Edward, I think he is.
My question is it easy to check? For example, you mentioned, for example...
whether that's holds? Yeah, so we have actually a couple examples that in which, yes.
Going beyond the convex problems or...
Sorry? Yeah, yeah.
Any other questions? I had a question. Is it repeating? So, you mentioned one of the application is that you can recover this ground truth theta and the parameter theta. Do we know if we can actually recover the ground truth theta? Because each FI is looking at only like a part of it.
I mean, each FI is looking to exactly the same one, right? I mean, that part of the model, right? Like you have this, and correct me if I understand your question well, that, I mean, every single client, let me just go maybe back to the algorithm.
So yeah, maybe I can clarify a little. So what I mean is each algorithm, each client is looking at the personalized version of the theta.
Yes.
But potentially there is one global theta which is like the best theta to personalize from.
Yeah.
Do we know if we recover that theta as well?
So I mean, under the assumption, every theta that you find, like under the assumptions that we make, every theta is the right one. For like more general setup that we cannot directly guarantee that, but I guess, I mean, if you design your algorithm well, and the thing is here we do only take a single gradient step, so it should be the case that it should be extendable to more general setup, and I believe that if you kind of set your assumptions straight, even in the more general setup, you can exactly recover that.
If there's no questions, let's thank Sam again, and we'll break for a short coffee break now for 20 minutes, and see you again at 11. talk by David. David is a researcher and entrepreneur with a focus on combining AI, climate change, biodiversity, finding impactful solutions for addressing the need of local communities. He is the founder and executive director of Gain Forest, and he's done a bunch of more stuff, run a lot of competitions, and I'm really excited to find out what he's talking about. Thanks, David.
Test, test, test. Oh, okay. Wonderful. So, to get started, yes. I want you just to take, we just had all a coffee, we relaxed a little bit, we had wonderful first 3 talks today. To just close your eyes for a second and listen to the sounds of nature here. What do you see when you imagine nature? Who sees like oceans? Jungle, green, forest, mountains, desert, people. So what I want to get with this point is basically that we often see nature as something green, something like that is there, but we don't see the people that are part of nature, that are often collecting, living, and depending on nature. And this data set that you just hear, the voice of the forest, the sounds of the forest, were collected by the indigenous Kayapo in Brazil. And I think this is a really big problem, that we're disconnected from the people that are living in nature, and therefore we are oftentimes taking away lots of natural goods and commons. And we see that when we feel and hear nature just now, we can all experience its implicit value. And nature is essential for human existence and good quality of life, but most of nature's contribution is really not fully like replaceable, and some are irreplaceable. And we see that when we talk about nature, that it's oftentimes coming from COP, of course, we'll talk a lot about carbon and carbon storage, but it's way more than that. It's like provisioning features, supporting features, cultural and regulating ones. And we have really not taken good care about this public common. We don't really value it. The natural world is actually deteriorating in rates unparalleled in human history. We're lacking tons of funding to preserve and fund conservation. And the question is why? So, of course, the United Nations and a lot of our policymakers know that nature needs to be funded. And they have pledged a lot of money into that. So this is called results-based payments, for example, for forestry. But the problem is that when you want to monitor the impact of natural world, or like if you want to measure nature, currently the measurement is really slow. It's overlapping land claims. There's a lot of trust that is not existing, which makes the funds inaccessible for the communities that just collected the data. So currently there's a lot of drive in data-driven carbon credits, where a lot of people want to collect tons of data from the forest in order to take advantage of this challenge and make an opportunity. And the problem here really is that tons of the data that is existing of forests, of course, are in the global south. And oftentimes the demand now is very high. But if you look at these 2 maps, on the top, this is the global GDP for the world, and on the bottom, this is like the amount of nature. It's basically a mirror map. So there are demands in the forest conservation community and policymakers to pay for forest data. So if you listen again to this one, this is a forest very close to the forest that you just listened to. And now you hear, for example, no birds. Quite silent and quite scary. And the reason why this is the case is this is a forest that just focused on carbon and didn't measure anything else. So this is a eucalyptus plantation that is only planted for forest and timber plantation. And this is what happens when you just measure one value and don't go to the field and collect data on the ground. So we kind of need to collect tons of data in order to properly value and protect our forests, to make sure that we don't do stupid decisions such as only funding monoculture forests, but actually value it as a whole. So we need to collect local data, like field-based data here, wildlife cameras from the environment as well. And the people who should collect it, of course, are the indigenous people. People are local community members that are living on the ground and should receive a payment for the data they're collecting. So the question is, okay, wait a second. Can we not just use remote sensing, measure everything from space? Why do we need to deploy really complicated human resources on the ground in the field? And this is something we tested out. So our remote sensing algorithms actually quite good enough right now that we can actually replace human labor on the ground. And we looked at several communities around the world, one in the Philippines and Lobo Batangas down in the south, and then 6 sites in Ecuador where we measured every single tree and compared it to existing maps of carbon data sets that are derived from satellite imagery. So we went to the field in the Philippines, paid out local community members, 6 people for 8 days to measure 1,500 trees where we know and understand exactly what is the diameter of the tree, the height of the tree, the species of the tree, and given that these measurements, we can derive the estimated carbon that is on the area. So how that works is usually, it's very simple, and this is how all these carbon credit projects work. You measure the height, and you measure the diameter, and from that there's something called an allometric equation in environmental science that gives you an above ground biomass estimate per tree, and then you can basically aggregate that of the area, and then we compare it with the public data set that is derived from remote sensing. And we can see, for example, when we do this, we can derive the above ground biomass density from this area, and we compare this with satellite-based data sets, and they are 9 to 16 times overestimated based on what we have measured on the ground. So satellite data is really biased right now, and that is not just in the Philippines. This is here the error rate, but this is also when you do this in Ecuador, we have overestimations based on current remote sensing data that is just not acceptable to do proper policy methods and evaluation. And the only kind of country that hits pretty well is the United States. And the reason is really, if you look at all the biodiversity data that is out there that science and the scientific community has collected over the last hundreds of years, and you would plot and resize the country depending on the biodiversity data, the world would look like this, right? Most of the data has been collected in the global north, in North America, in Europe, and actually the place where most of the data that should be collected, that is about nature, like in Africa, in the rainforest, in Congo, or in the Amazonas, is not connected. And that is, of course, due to lack of bias, infrastructure, lack of resources. So the idea here is really, okay, can we design, based on the lack of data that is needed to improve these algorithms, to make them more fair, more equitable, can we design a framework, a principled framework, that values data and pays out local communities for collecting it? So we looked at existing data valuation approaches in the past. How did people value data? There's, for example, query-based approaches where there's just a flat price on demand, Cotres et al. From 2012. People did auction-based data valuation and model-based data valuation. But really the question we want to answer here is, given X dollars, how should each data point be paid out to reflect its value, right? So our desiderata for kind of this data valuation would be like follows. Well, it would be nice to just have something that is combinatorial, because data often comes in multiple sources. We will see in a second, especially in nature, it comes in multiple different kind of varieties that are really hard to align over. it would be nice to have a task specific, so maybe the value of the data or the payout of the data should depend on the task it is trained for. And of course, it should be cumulative, the data point can be used multiple times, and equitable, because the same data point that contributes exactly the same output to one algorithm, and if there's another data point that does exactly the same, it should be a symmetric value. So we looked into this, and we thought, okay, combinatorial game theory, cooperative game theory is quite a good place to start here. So we take the task as a machine learning output. Okay, we want to improve this machine learning algorithm that is currently lacking in like accuracy, as we saw on CARM estimate, because it's lacking the data. How can we model that potentially as a cooperative game in order to incorporate all its potential combinations? So what we came up with is basically on the left side, each data point is a player, and then the algorithm itself is a utility function that evaluates its performance on a specific task. That could be like the validation data set of like how good it is to predict this cat. And then you can model this as a cooperative game that is played among these players, which is each data point a single player. So task specific, we reduce that into a profit allocation problem. Basically, okay, the machine learning model provides a certain kind of profit, and that needs to be rationally equally distributed back to the data points. And then for cumulative and equitable, what allocation scheme basically we're asking satisfies all these desiderata? And it turns out there's only one unique solution, which is the Shapley value, that satisfies these four properties. And the Shapley value is straightforward. It's basically given a number of training data points, and like let's say D is the training data set, and S is a subset of the data set, except for the player set B that we want to value. Then what we do is basically we input that data point into a utility function, which is the algorithm, the machine learning training, or the validation data set, and we calculate the marginal contribution of that data point. And what it does is basically it does it on average for that data point. So the average of all possible subsets, what is the marginal improvement? And Shapley has shown that this actually satisfies several properties. One is it's equitable, so every data point that does exactly the same impact will have the same value resulting from that, and it's cumulative. It has this really nice linear property. So the problem with this approach, though, is evaluating U, the utility function, because it's the machine learning like training and task is quite expensive, and by itself, Shapley is already has exponential complexity, so that doesn't properly scale. So what people have done in the past to improve Shapley computation is basically approximated as an expectation of the average, so expected marginal contribution, and then you can just take some random subsets, and you get some, using Monte Carlo approximation, some approximation boundaries. And then you can see, for example, that this is an epsilon delta approximation to the true Shapley value. So for machine learning specifically, and that's actually the beauty of formulating the Shapley value as formulating a machine learning task as some kind of a cooperative game, is that these utility functions are now specific to certain kind of machine learning tasks. So we can leverage the specificity that machine learning has in order to speed up the algorithm even further. One, for example, we can leverage several characteristics. We can we can proxy the utility function. We can say, for example, assuming that the utility function has certain kind of like properties, like locality, like maybe it's a k-nearest neighbor, we can improve the algorithm. Or if the utility function is kind of differential private learning, it has a stability feature properties, then we can also improve the computation. So let's look at k-nearest neighbor. So assuming that the utility function is a k-nearest neighbor, all we need to do is actually just, given the training data set, and we want to compute the Shapley value of a certain point to the training data set, we need to just query to the query point, sort the training data set, and then compute a majority rule. Sorry, that lags. So basically, the intuition is here, when we leverage the locality of the algorithm, then many of the subsets, let's assume 1 nearest neighbor, many of the subsets, when you, for example, want to add that point into that subset, is 0, because it's not going to be considered anyway in the Shapley computation. So this is 0, this is 0, this is 0, this is 0, for example. And all of these are 0, so we don't have to consider, we don't have to try out everything else. And we can derive a decently fast algorithm that can provide us the exact Shapley value, given that the algorithm has a certain kind of locality property. And the algorithm looks like this. So we sort it once, and then we calculate it recursively using this function. And it would provide us ON, and the sorting itself is n log n. So we can calculate exact Shapley values, given that it's a KNN algorithm, in n log n time. And that's, of course, much faster than if we would do it like brute force, where we know we have to exponentially evaluate the Shapley value. So it's 2 to the power of n, and then we need to sort it every time we do this. So that would be the baseline that we compared, given the KNN Shapley algorithm here. So that works on millions of data points, and we tested it out. For example, if you have 10 million data points, and you assume a KNN Shapley value on 152 gigabytes, it would take 44 seconds on a single machine to compute the exact KNN Shapley on this data set. And that is much faster than we would run, for example, Monte Carlo sampling. More work has been done since then. So that's a list of more data variation algorithms that have been published and discussed, and I'm looking forward to the talk of Brian, who will introduce some of them. But now I really want to show you from, okay, we have this really nice framework where we, okay, decided some on desiderata. Now let's go to the field and see if we can implement that and what do we learn. And we are partnering basically currently with 23 organizations on the ground, paying them with this Shapley-based approach. They're collecting data. We're computing the value of the data given some certain machine learning tasks and paying them out back. And what we see is there's a lot of challenges that are coming out that are not considered before that I would love to introduce this to the community, see if there are certain kind of approaches that could be used to tackle this. The first one is that when we value, the infrastructure of data collection is very crucial in the given system of designing these incentives. For example, many of these communities don't have proper internet connection, so the data collection itself will happen in a delayed process. So we implement certain kind of technology to allow them to go into field, collect pictures of trees, but that needs to be very robust and offline. And that's, for example, how it looks like when you go to the field and you want to upload the data. Oftentimes, we provide them with the mobile phones, and the upload itself is delayed. So that's a challenge. What we do then is basically, whenever we have internet, many of them are unbanked. So we are connecting them with mobile wallets on the blockchain in Web3 and pay them out in crypto for now. And we have local partners that then directly translates that data payment into their local currency. So the problem here is also that when you provide the Shapley value as a payoff method for these communities, there are certain kind of problems that come with it, even though it comes with really nice desiderata, that makes it unsuitable on the ground and in the field. One is, for example, that community members might not understand it. It's kind of, even though it provides us with these wonderful guarantees, it's not clear to them, and it's kind of hard to interpret. And that causes, for example, when we're in Ghana and we are paying out with the Shapley value, a lot of mistrust. One of the things we also learned when designing these data payout games is that when you pay out the money only once and you don't communicate that it potentially could be a repeated game, that there are certain kind of incentives that will steer towards gaming you, right? Because like you're one of these people who will basically come to the ground again, promise them like some money for their data, and you might not come back. So there's a strong incentive to cheat on you and take most advantage of you, while compared to what we learned later on, when you promise them that it's a repeated game, like you come back and back and back, it will steer the incentives towards a more favorable position for you. Also, paying out people is not necessarily a strong incentive. In many of these communities, there are incentives that are non-monetary. For example, collecting data itself can be used as a cultural, social, and educational benefit. Elders could walk around, show youngers like the forest and the area, engage in like culture exchange. So there's a strong incentive actually to do this if you design these programs not only with a monetary incentive in mind, but also in a cultural context. We always think we can sample the whole area like in whatever way we want as someone like as a person from statistics, but in areas that are, for example, based on nature, certain kind of parts are completely inaccessible, and even if you want to explain to them that it makes sense to go in this area and this area, they will not. So here in the rainforest in the Amazon, for example, we can only sample in the blue paths, which are traditional paths, and not the other paths, because it's just inaccessible, there's no willingness to enter, it's just a lot of hard work. So that's also something to consider. In the end, of course, we work with a lot of different kind of data modalities, so how do we fuse it? We see that several approaches, when we fuse them together, of course, make more sense and improve the accuracy of algorithms. But then on the other hand, if you fuse modalities that are image and field-based, you will come to problems that are alignments. For example, like predictions of bounding boxes of trees won't align properly with GPS coordinates of the collected data points. So this is going to be also a hurdle when it comes to different kind of modalities to combine them together to make them effective. And one of the things we also observed, we provided them with drones to collect their own drone data, that there is incentive to cheat and to pretend like that the area is, for example, more forested than other areas, especially given that when the forested area is paying you more than not. So there are attack vectors to modify these images from communities when it comes to decentralized data contribution. And then the question is, okay, how do you prevent these attack vectors? And we had some work on metric learning and classifiers to classify if a drone image is very similar to a satellite image, and assuming that the satellite image has a higher trust, we can trickle down the trust to that decentralized collected drone image, because we can basically classify if it's the same or not. Okay, I'll skip that. And one thing which is also really interesting is that these communities have wonderful knowledge that is really hard to access and structure traditionally. So for example, this is a participatory mapping of all the Brazil nut trees in their location, and it's written on a map, so they can just produce it. But then when you really want to leverage that into machine learning algorithms, that's kind of an unsolved task. So one of the things we noticed, for example, when we compared the locations with satellite data, is that these trees stuck out, so we could extract some visual features to train a CNN, but they have so much more wealth of this knowledge, and it's really like an open research question. How can we properly structure that wealth back into our busy digital systems? Last, data ownership. This is traditionally something that when we talk about hospitals, the hospitals want to have the data based in their hospitals. And in nature and indigenous communities, we have a similar scenario where it's really, really difficult to basically collect natural data in communities and transfer the data into European or US American servers, because it will potentially create ethical conflicts and also like conflicts with policymakers. So there's a strong incentive to keep the data locally stored. So with that, I conclude. I think there's a lot of future work that we can look into, for example, how to fuse more and more upcoming data modalities into the system, and also ensure that as technology is getting better, how do we still can maintain fair data payments to local community members, don't make them obsolete, because much of their contributions are really valuable to steer our systems properly, to make them ethical, and to also benefit these communities on the ground who are stewards of the forest, and that would be a wonderful way to preserve and contribute to conservation. So I'll skip that. These are like new methodologies to collect biodiversity data, and I'll end with, I'll end with this slide. So some lessons learned on the ground trying to implement data payments is we need to be transparent and open when communicating the data payment strategy. So the payout game influences a lot the behavior and gamification elements of the local community members. It's really important to co-design the game with the local communities, especially when it comes to data ownership, to scenario-specific utility functions, and build tools that satisfies them and not just build tools that no one else is going to use in the end. And I believe nature conservation is a great place for the collaborative learning community to look into that is outside of healthcare and is still unexplored and can provide a lot of interesting last-mile problems that arise a lot of now interesting research questions. So thank you so much for your time, and I'm open for any questions.
Yeah, while the mic's reaching.
Yeah, I think it's great to pay people for data and really critical.
Thank you.
For other works of, creative works of various kinds, people get paid over a long period of time.
Yeah.
So it's hard to value your data from the get-go. I don't know how valuable this could be, but maybe it turns out to be really valuable, and some downstream user, it just becomes more and more valuable. So you would like to have the ongoing stream of revenue. You'd like to have provenance. You'd like to have a whole infrastructure set up. I'm just wondering how much you've been thinking about that.
A lot, actually. And I believe this is one of the critical, I think even almost groundbreaking ideas of paying for data in conservation is because right now conservation has two ways to finance itself. First, donations, which is not scalable. Second, forest carbon credits, which we saw are fishy. Creating actual value in the digital economy and maybe charging an API that can pay a subscription fee and that pays back to the community members who collected the data is a predictable potential income source that will last longer than donation of forest carbon credits. So the question here really is, I talked a lot about the supplier side. These are the people who provide the data. I didn't talk a lot about the demand side. Where does the demand come from, right? And that's something that I've been thinking a lot. Demand can come from pharma companies, because many of these, especially indigenous wisdom parts of plants are medicinal purposes. That is right now unstructured. Like, we don't know anything about the Amazon. The Amazon is the size of Europe. In the continent that is the least known continent in the world, and that's the least known area of that continent as well. So there's a lot of knowledge that's gathered for pharmaceutical interests, for example, that we can take and benefit in. So if we can solve the demand side, I believe it will be as simple as a database of who contributed the data and a paid API access that basically channels the funds directly back to the people who contributed. Because if you can track the provenance of each data point into the database, you can distribute the money back.
So you mentioned differential privacy, and I was wondering if, because under differential privacy, you bound the contribution of a user or a training example. And then the payoff is going to be a little weird because everybody would be essentially contributing up to that epsilon leakage by differential privacy. Have you thought about it, how to incentivize in that regime?
Yeah, so when the algorithm is stable, like it has a stability property, then as in differential privacy, you can less track a single individual contribution. The values will basically equal to each other.
Yes. So I can imagine that for each of this participation, you will have different participants coming in at different time. Yep. So how do you value them, right? Acknowledging the fact that they actually come in at different time and they may leave.
Absolutely. So that's actually one of the big open problems. Like, if you want to make it a repeated game, especially, and you have different participants coming different times. Right now, we do a non-perfect solution. We basically cut it and batch it again and recompute it, right? I think there is much more efficient ways. We can cache previous results. We can derive them from. But as of right now, this is the like most stupid way we're doing it.
I guess one comment I may have is, you know, for the issue on repeated payments, this is something that we see in federated learning as well, especially if you want to look at all the various iterations, right? Where in the earlier moments you may contribute more, but towards later you might not, and vice versa. So maybe some literature from that aspect in terms of payments would help. Yeah.
Mm-hmm. The problem is, and I really like your work on this, is that the shareware itself is not robust against potential attacks, right? That would incentivize a duplication attack. Is a classic one to basically, you can just duplicate the data millions of times, and then because of the fairness property of the shareware, it will be all the same value, right? So these are the things that we need to consider when designing like first come, first serves, like incentives, but it's a really good point.
Can I ask Alan to set up, the next speaker to set up the, oh yeah. Yeah, are there any questions while Alan's setting up? Maybe I have some, one, I guess, easy question is, have you seen any measurement of the influence of these benefits of implementing these kind of systems?
Yeah. When you do one-time payment, people cut down the forest afterwards because they don't expect you to come back. So the reason we do this is, of course, first, there are two things. We want to improve the algorithms that are lacking accuracy right now, but then also we want to generate an understanding for local community members that this tree pays you, so you better not cut it. So if it's a one-time payment, we saw that after 6 months, they're just gonna cut down, like it happens very much that they cut down like parts of the forest for a parking lot, which is unfortunate. So a continuous repeated game actually so far has been much like more successful in preserving certain areas than when it's like less better communicated. So I think communication is really, really key. Trust is really, really key. Local, like communities in the Global South has experienced so many one-time games that they've got enough of it. So really the thinking has to be in repeated games. And as Michael said properly, it's really difficult to value that like in the future, but potentially you can escrow some money, promise them that when you start the relationship, and then over time distribute it like in small steps.
Reputation systems.
It will also be cheaper because the incentive is not as strong to cheat you, right, as it's repeated.
Thanks so much, David. ENS Kashan, and completed a PhD in applied maths in 2016. His research focuses on computational statistics, Bayesian inference, and applied probability. Thank you.
Yes, that's good. Okay, so.
Can I have the presentation? It's not?
Yes, thank you very much. Okay, so thanks to the organizer to invite me, okay, to discuss about some old work, in fact, okay, because somehow, I will discuss, in fact, mainly the work of, so yes, the pointer does not work, right? Okay, so it's part of it. So I will somehow, in fact, explain the big picture about Vincent Placier's works, which was a PhD of mine and Eric, and also with Maxime Vonneau, which was a postdoc at some points, and now he's at Criteo, and also, it's also joint work with Nikita Kotoyevsky, and yes, that's okay. So, just a brief summary of this talk. So, okay, I will start by basic motivation of my work, mainly on this kind of federated Bayesian inference that we didn't, in fact, heard yet. Then, okay, I will provide you some brief summary of two federated Langevin samplers. That's okay. We have, in fact, promotes and develop, which we name QLSD and FALD. And okay, I will end with exactly in fact, the main content of this talk, in fact, which was in the abstract about personalized federated learning, and okay, with an algorithm which we name FET-POP, but in fact, Sam already introduced a bit about this topic, and it will help me a lot in introducing this methodology. All right. So here, in fact, so I'm basically, in fact, aim to make uncertainty quantification. So here, I suppose that I have a probability prediction. Based on this probability prediction, in fact, people are interested in making calibration on your prediction. So here you can think about test your model on the likelihood, or using Breyer score or expected calibration score, which in fact I don't provide you the explicit expression, which is a bit very long, and I don't have much time. So, but basically, in fact, it gives you the discrepancy between the confidence of your prediction and the real accuracy. But here, okay, all this uncertainty, all this score, in fact, are based on your model. And here, what I'm interested in is to construct this model using Bayesian inference. So I will not debate about the use of Bayesian inference for deep learning, because here, in fact, I'm just focusing. I want to apply Bayesian methodology for constructing my prediction, my probabilistic prediction. So here, just for the notation, I suppose I set a model, on my label given my features, parameterized by theta, which is specified, let's say, by a likelihood. I choose my favorite prior, and given my train sets, I can define now my posterior, which is simply proportional to my prior, and times the product of my likelihood at my given date. All right. And then, based on this prior, I can define the predictive distribution as it is with my posterior distribution, which is just the integral, of my model against my posterior distribution. And somehow we can see that you average your prediction given your posterior knowledge of your data, and that's somehow the rationale behind all the Bayesian inference. And here, you can see that the main challenge is to sample from the posterior distribution given the data, and an algorithm to sample from a distribution which is non-optimative constant, which people in the room work a lot, is a Langevin algorithm. So let's say that now I denote by minus log of pi u. It's what I call a potential, which is a term which comes from physics. But here, in fact, I can decompose my function u based as the sum of functions. So v0, in fact, stands for the minus the log prior. And now, I can take a sum over my data of vi theta, and just vi is, the log minus the log of L theta of yi given xi, where yi, xi is just one given data point. Now, based on this notation, I can introduce you the Langevin algorithm just to try to get approximate sample from this posterior. So here I just define a Markov chain theta L as, okay, theta L plus 1 equals theta L minus gamma gradient U theta L plus square root 2 gamma ZL plus 1. So here, gamma is my step size. And so it's, okay, you can see this. In fact, the motivation behind this scheme is that the discretization of the Langevin dynamics, that you know that it converges well to the posterior. But still, okay, you have some bias. And still, you can analyze, in fact, the explicit convergence band for the scheme to pi. And also, you can replace the gradient by some stochastic gradient as SGD. All right. But here, now, in fact, I want to apply this methodology in a federated context. So on each client, okay, I suppose that I have some local data sets. Okay, so here, so it should be not J in dk, but K. So I have, in fact, individual data sets. And on each, in fact, client, I have NK data. And based on this local data set, I can define, okay, what is called local posterior. So it's just the posterior distribution associated to each client based on their data. All right. So here, again, in fact, I could decompose also the potential as a sum of individual potential. All right. And okay, but here, okay, I want to define a global model across all my agents. And Bayes' formula just tells you that, in fact, the a posteriori distribution of your global model is just, okay, proportional to the product of the local posterior. Okay. So here, my main objective here is to try, in fact, to adapt the Langevin, okay, methodology to this federated context, akin, in fact, what is done in federated learning, but for stochastic optimization. All right. Just, okay, for somehow a teaser. So, in fact, there have been, in the literature, other approach, okay, to try, in fact, to get, to construct some sample from this global posterior, especially, in fact, with what is called Bayesian fusion, okay. Or also, in fact, it has been proposed to, in fact, trying to get a sample from the local posterior by constructing, in fact, Wasserstein barycenter based on this sample. And in fact, we have proposed in a recent work with a PhD student of mine, Maxence Noble, in fact, a scheme to try to construct, in fact, Wasserstein barycenter based on sample from pi_k. So if you're interested, just we can discuss it later. But I will not discuss this work because it's very technical and so. But here, okay, I want really to focus on the development of Langevin sampler for sample from this global posterior. So here, in fact, the main, in fact, rationale and okay, of this type of scheme is that as, in fact, usual federated stochastic optimizations, I have a current iterate tk, which will be, in fact, my current, let's say, sample from my MCMC algorithm, my federated MCMC algorithm. The server sends back, okay, this sample, okay, and approximate sample theta k to the user. Okay, now, in fact, the user can perform local operation, and based on this local operation, okay, they send the results to the server to update, okay, the next parameter theta k plus 1, and okay, based on this, so the server now have computed the update theta k plus 1, and the theta k plus 1 is sent it back to the to each client, and again, and somehow, in fact, it summarizes the schemes that we have developed, the federated Langevin sampler that we develop akin to what is done, in fact, as I said, to stochastic optimization. So here's the first scheme that we suggested. So it's, in fact, somehow the same as in quantized SGD. Compute, in fact, okay, so I will be very quick then. So the client, okay, compute their gradients associated to their data, they compress the gradient and send it back to the server, which in fact perform a local step of compress SGD, okay, but here you just add the Gaussian term to in fact use this, so you can see this as a federated quantized names that we put on the algorithm. And okay, the second methodology that we have analyzed is, okay, somehow akin was local SGD, where in fact, instead of SGD on each client, you perform in fact local launchpoint step associated with each local potential, okay? So here now, I really want, in fact, to move on what we have done on personalized FL, because somehow it responds to also some talk. So here, as I said, so somehow on each client, okay, we have some local likelihood. Okay, so what's based on the dataset decay. And here, what we try to construct, so here we have the local, obviously posterior, based on the local likelihood, but somehow we assume a global model across all the clients. And somehow for personalization is a limitation. And here our idea, okay, in our work with Nikita, Maxim, and Hanson was in fact to introduce personalization by the means of local variables seen as latent variable. Okay, so more precisely, so here we suppose that the local likelihood, okay, is the integral, is the marginal, okay, of across, in fact, latent variable, which depend on the clients, okay. So here now, I suppose that, in fact, I have a hierarchical model where, in fact, the data come from, in fact, the likelihood of the data depend on a global parameter phi and local variable zk, okay? And I put now, okay, now it's specifying my likelihood, and now I put a prior on my local variable zk, and I put a prior on my local variable zk, depending on an extra parameter beta, which are, in fact, global to all my clients, okay? So here you dissociate really, in fact, as in some talks, somehow you have, in fact, two levels, one which is, in fact, global and the other one which is local. All right, and here now the parameters that you want to infer, okay, is, in fact, the global parameter, okay, of the likelihood and the parameter of the prior on the zk, okay. And so here, in fact, you can see the problem as marginal likelihood, marginal likelihood problem, all right? And so here, in fact, now the main issue, so if you can write this problem as now a federated stochastic optimization problem, but here, okay, the function fk or fi here is just minus the log of the marginal likelihood, the individual marginal likelihood, okay, based on the data di, all right? And here, okay, just to a teaser, so what is important is that let's say that you have optimized now this function, okay? If you have access now to phi and beta, okay, you can in fact have access to you can use an empirical based approach, and you can also try to sample from the posterior of the local parameter of the local variable zk, and gives you in fact a way to get personalized uncertainty quantification. But now, okay, let's focus on trying to optimize this function. So here, it's, as I said, just somehow a federated, you can encompass this problem as a federated stochastic optimization problem. And here the main issue is that, okay, the function are some marginal likelihood, but okay, you can use, in fact, usual tricks from the field to just write now, to use the gradients of the individual function fi as the integral of the gradient of the log of the data given the parameter times, okay, the local posterior. And now, okay, to get, in fact, MBS estimator of the gradients, you just need, in fact, to ask to each client to get approximate sample from their local posterior, okay, which is personalized. And from this sample, okay, you can get MBS some estimator for the gradient. So here it's for beta, but it's also for phi. Okay, just so you end up with the algorithm, the natural algorithm associated with, and just some toy data. So we compare it on a very toy example here. So we, in fact, we compare it to, at that time, okay, let's say a state-of-the-art algorithm, which was FedRep and FedAveraging, which, in fact, so you can see that we were capable, in fact, to get really more accurate estimation for the local parameter on this toy example, which somehow is cooked up to work, okay? And also, so we also had some application for classification, but I wanted really to illustrate this methodology for uncertainty quantification, where, in fact, based on the posterior distribution, the local posterior distribution, we are really able to get personalized, in fact, uncertainty quantification from this methodology. So we use it, in fact, for calibration, so to get personalized calibration error and on MNIST and MNIST and other data. So thank you very much, and if you have any questions.
Any questions? And meanwhile, Praneeth, can you set up? Yeah, maybe I can ask a question. How do these how does the quality of this uncertainty quantification compare with if we pooled and we just trade a standard Bayesian model?
So here you can use, in fact, the data on all the clients also.
I'm just curious if usually in the proofs of these federated convergence, we prove in terms of like the accuracy convergence. Can we also prove something about the uncertainty measures of uncertainty will also converge to as if we were computing on the pooled data?
I'm not sure that I understand completely the question. So here is you want somehow to construct a global model and you dissociate somehow.
I'm just curious, like how much does the distributed data hurt for the uncertainty quantification versus if we didn't care about privacy and we just used a centralized method?
So I don't. Yeah, you want somehow you assume somehow some kind of heterogeneity also across data. So here, in this case, it's I don't really see, in fact, how it goes.
I see. Yeah. So we next have Praneeth Vepakuma. Praneeth just defended his PhD at MIT and has started as an assistant professor at MBZUAI. He's also one of the local organizers of the workshop. So thank you. He works on distributed and private computation with a focus on responsible, trustworthy AI. And he co-founded a non-profit called Integrated Distributed that won the Financial Times Digital Innovation Award for its work on financial regulatory compliance. He's also one of a bunch of other awards.
All right, yeah, so today I'll be talking about the embedding release problem. Let me explain that in the context of collaborative learning. So looking at the current scheme of techniques for privatizing machine learning models, so for the release of a model, or like the model weights, in the context of, say, distributed or collaborative learning, like, for example, like in federated learning, there's been, and with privacy guarantees, there's been like different ways of perturbing the part of the training process so that the resulting model has differential privacy guarantees. And the perturbations have been tried at different parts of the whole pipeline, and the ones that stuck more the test of time have been the ones that focused on gradient perturbation. So how are gradients perturbed during the learning and specifically the optimization process of learning a model? So this is great. I mean, there's certainly a lot of progress in that area. One part of privatization in this setup that has been somewhat understudied relative to the huge body of work you saw with model release is the question of privacy for embeddings. Or representations at different layers of the model. There's a reason why this is understudied, because if you think about the weights of a model, they are a statistical estimator. But if you think of the representations, these are one-to-one functions, so it's more like a local privacy kind of problem. So it doesn't seem like the obvious thing to privatize first if you want to have high utility in the distributed setting. So the approach we take, that said, there is benefit to privatizing, figuring out mechanisms that privatize embeddings or representations of different layers of a model. But what are the benefits if one could privatize? What are the benefits? There have been, again, somewhat understudied schemes of collaborative learning, which is based on representation sharing as opposed to weight sharing, which is very popular in federated learning. So these methods have, or different variants of these methods or designs have benefits in terms of higher resource efficiency for the client. It also helps purposes like personalization that people have been talking about and so on and so forth. So this is more resource efficient. So the focus of this work that we call power learning is some sort of a modification to the distributed training regime, the design or the protocol of distributed training, as well as privacy guarantees at the embedding layer. So let me just explain the systems interactions involved first before we go to the details of the method. So the system interactions, assume there's a hospital, which is a client, which is resource constrained, and assume a large pharma company, which is not as resource constrained, and they would like to collaborate to train a large machine learning model. So the different components of the hospital's model involve a piece of the privatization network, or the privatization piece. And the client in this paradigm would also have some sort of a surrogate model, which it could use to somehow steer the model towards a reasonable utility. And then the pharma company receives private embeddings instead, this is the representations, which are privatized through the power mechanism. And the pharma company then continues its large model training and so on and so forth to get the final utility of its maybe like a task for treatment plan design or whatever its pharma task is, the ML task. So some more takeaways before we go into the details of how we privatize it are as follows. So this is more in line with what happens in personalization, right? So if you could privatize in this setup, you would only have to privatize once and do like a one round of lightweight communication. And then, so it's not collaborative at every epoch or at every round, So you just privatize and release the embeddings. This is more in line with, say, some notion of personalization or like the large language model or like the BERT embeddings. It's like an embedding release problem. The other takeaways are, of course, we are trying to give formal privacy guarantees. The utility, we don't have guarantees. We show that empirically. There's two other takeaways, which is more, this is a good context to discuss here because there's been some very nice discussions around incentives in markets and data valuation and so forth. So one question that remains there is, what is a utility function that you could design for a data valuation scheme where the utility function depends on privacy? What is the notion of utility in terms of privacy? What does it mean for a record to be easy to be privatized or hard to be privatized? And how would you value this and give costs and disperse payments accordingly. So we get some benefit of that, and we also show that in this kind of a scheme, we could do few-shot learning, which is we can try to identify those specific records in your data set which are easier to privatize at a high level of privacy, and then you can only use those records and not use the rest of the records for training. So it kind of enables few-shot private learning. OK, so now comes the question. What is happening in the privatization network? Because the rest of it is more like standard ML. Is there some notion of a privacy loss, and how does the training need to be done so that you can guarantee and calibrate privacy levels? So we go back to like the simplest network ever we could do, and then we kind of stitch it into more modern ML. So the simplest network one could think about is the equation you see on the top. So given your data set, this is if you can learn an operator H on your data set, and then if you do a power, hence the name power learning, if you do a power of the operator is a matrix, so you do a power of that matrix, and then hit it to your data set, and then you get the output Z. Now comes a question. So this is like a simpler than a linear neural network, because this is like a trivial network where all the networks have the same weight, and you're just hitting by P. There's no activation, nothing. The H could be a nonlinear function that's set of X, although the operation is being applied in a linear way. So now the question is, how is this operator H supposed to be designed? What are those properties? And what is the power P supposed to be so that we can guarantee privacy or differential privacy? Secondly, since this is way too simple a projection operation, we then plug it into more of a ML kind of a setup where now we have a privacy network, which is a standard deep network that learns representations. The output of the representation is on which the power operation is applied. So you take the output of your representation, and then you do the power operation. But that said, differential privacy has a post-processing property, but it's not immune to pre-processing. So we cannot just start with the output and assume you'd have privacy guarantees for your input. So we have to figure out how we design the weights of this privatization network, and then get the representation, and then pass it through the power mechanism, and then you have a privacy guarantee. So how is this put together? So the motivation comes from a classical principle in analysis, or like in probability, which is the notion of learning transformations. If you knew the PDF of your data, this is called the change of variable theorem, and when you apply it to like densities, it's called the change of variable theorem applied to probability distributions. So if you had a distribution for your raw data that that exists, and you apply some transformations, the question is, what is the PDF after the transformation? That's what the change of variable theorem deals with. Why is this kind of a nice starting point before we do the rest of the math? Because the differential privacy definition is defined on probability distribution. So we need to work on probability spaces in addition to the transformations that we have, so that we can say something about how should the transformation be designed so that you end up with a privacy guarantee. So this is a kind of a visual, right? So it's of course univariate. So if you had a blue distribution that exists, whether you know what the distribution is, what it is or not, and if you apply, say, the exponential transformation, then you get this new distribution that you get through the change of variable theorem, for example. You can have a version, well, it's hard to play this now, but you can have a version of this in, again, in classical distribution theory, on like going from a uniform distribution to a Gaussian, for example. This is a multivariate. But in the 2D case, there's a very popular transformation called the Box-Miller transformation. So this is another application of, for example, the change of variable theorem. OK, so what is differential privacy? Quick one version of there are many equivalent definitions. One version is if you had two neighboring data sets, the notion of neighborhood is up to your design. One possible notion of neighborhood has been the Hamming distance, but if you generalize the metric to something else, it's called metric differential privacy. So if you have neighboring data sets, and you apply a query F, and a query M, and then you look at the probability distribution of the output of your queries applied in the neighboring data set, and if those don't change beyond up to an epsilon, h bar epsilon, this is called pure differential privacy, and you can have like a slack parameter, which is an additive probability under which the DP guarantee does not hold, and that's called approximate differential privacy. That's epsilon delta. And there are many more variants. As you see, all of these are defined in terms of probability distributions. Hence, the change of variable theorem and transformations are useful. There are also, there's a quick slide on different equivalent definitions of differential privacy. So you saw so if you just do, if you rearrange your definition of differential privacy, you can get a real-life instantiation of this random variable of how the loss behaves. And since we are guaranteeing dp with respect to some sort of epsilon parameter, this random variable, this random variable would always, if the probability distribution of that random variable would always be bounded between plus or minus epsilon. So this is the privacy loss distribution kind of an instantiation of what DP is. This has very nice properties via people working with PLDs, the privacy loss distributions. You can sample from PLD, and then the question is now if you have composition of transformations. People want to know how their privacy budget epsilon is depleting or not depleting and so on and so forth. And they don't want to be too conservative, because if you're too conservative, then you're losing more utility. You want to be as less conservative as possible. So that's where people went from classical DP to newer DP mechanisms like Renyi DP and zero concentrated DP and FDP and so on and so forth. So how is composition being done in a more accurate way when you are able to use privacy loss distributions? The beauty is follows. So if you have the privacy loss distribution for the individual components of the composition, and if you want to get the privacy loss distribution after the composition, all you need to do is a convolution operation of the PLDs. So you want to understand the PLD of a composition, you do convolution of PLDs. Convolution of privacy loss distributions is a lot easier to do computationally, because for any distribution, you need to just sample from individual distributions and add those samples. That is equivalent to a convolution operation. So this is very easy. So you can sample from individual PLDs, add them up, you get a convolution, you get the PLD finally. And this kind of a thing has led to newer versions of differential privacy, like Renyi DP or differential privacy equivalence in terms of information theoretic divergences. DP is equivalent to this hockey stick divergence being less than or equal to delta, where the hockey stick divergence is specified based on the epsilon. There's a hypothesis testing notion of differential privacy, which is an equivalent definition, which says if you run a hypothesis test in terms of an attack where the attacker is trying to guess whether a specific record is in the distribution or not, then you have a type 1 and type 2 error of the attacker's hypothesis test. So there's an equivalent definition of DP, and you see the epsilon delta plugging in. And you can have different trade-off functions of the type 1 and type 2 error, and then you have a trade-off F differential privacy based on your choice of trade-off. OK, so that's that. So now we've seen that everything is about distributions, as far as if you want to go towards DP. So we are talking about transformations. Now the question is, and we are also talking about the fact that you can generalize the neighborhood around the choice of neighborhood between your data sets to a different metric, which is called metric DP. And there is a notion of equivalent notion of metric DP called Lipschitz privacy, which says that if you minimize the norm of the gradient or the log of the probability distribution of your query to be, if you bound it to be less than equal to an epsilon, that's an equivalent notion of DP. It's called Lipschitz privacy. And this is these are both equivalent, so this is more computationally wieldy, because that's just a definition, but this is something you can plug into your optimization schemes and so on and so forth, the second equation. So now, how do we do this in terms of a neural network? So we've connected DP and transformations and change of variable theorems and outputs. So we derive that in order to learn for the power query, in order to learn the condition required so that upon applying the change of variable theorem, the output distribution satisfies the Lipschitz privacy guarantee that I showed you in the previous slide. That boils down to this specific loss that needs to be achieved, which we call the loss required for privacy. It depends on a few things. One is the Jacobian of your transformation. So it could be the initial neural network and then the power mechanism after that. If that needs to be under control with respect to epsilon. The F functions are basically nothing to do with your transformation. They're just a notion of how hard or difficult it is to privatize. It's basically saying, these are basically the densities of your raw data itself, the density of your data and your density derivative. So if you bound that to be less than epsilon, then you have Lipschitz privacy, and then we're set. We have the benefits of collaborative learning with privacy guarantees with the embedding release. But of course, to make it more exact and quantify the uncertainty, because DP is a probabilistic notion, we are having some density estimation terms that we're dealing with. So we do density estimation and apply the confidence intervals, and we get an updated calibrated epsilon, which is the final epsilon we have. So that's the power mechanism. And now I'd like to conclude by just showing a couple slides on results. So this is one example in terms of the benefit from understanding the cost of privacy, which is if I apply the privacy-preserving loss that I've derived that guarantees privacy on the embeddings, and I shoot for some epsilon that I'm asking for. But then this is a neural network. There's a lot of optimization going on. It's not going to guarantee that you would get the same privacy level for all of your records. So what we get now is a histogram of different privacy levels that one could, at an instance, could have guaranteed after the fact, at a post hoc, after running the power mechanism. And then, as you see, if it was very left-skewed, it would mean that you can guarantee high privacy for most of your records. If the result happens to be more right-skewed, it means you can guarantee not that high privacy for most of the records. So left skewed is better. But now if you have a specific privacy level, I don't want to break your privacy requirement. So if, say, your privacy level is 1, then I can, or 0.5, I can say you only need to use these set of records to the left of 0.5. And so that's a notion of cost or utility of privacy that one can plug in. It is an intrinsic cost that can plug in and say how hard it is or not hard it is to privatize any specific record. And you can plug in into like, your data valuation and market kind of schemes if you need a utility function for privacy. OK, and the final plot. So what happens to the accuracy privacy trade-off with respect to DPSGD, for example? So this is a tabular data set for like a churn prediction. We also done it for like forest fire data set. So the story is the utility privacy trade-off is kind of comparable with respect to DPSGD style techniques. The bottom is DPSGD, above is the power mechanism for embedding release. But then if it is comparable, where is the gain? Apart from the cost or utility function of privacy, the other gain is in terms of the fact that now we are able to do distributed learning with clients having just the personalization piece. So you're going to gain in like a lot of communication rounds not being required. You're getting one-shot release. You're getting, you're able to deal with more resource constrained client devices because now you can just have 3 layers on the client and everything else on the pharma company or like the server. So you get that kind of a benefit. It's from a distributed piece. OK. Yeah, so closing slide. There's a NeurIPS going on, but I was more excited to be here. So this is an advertisement for our NeurIPS paper, the main conference. There's not been much work done on DP guarantees for inference, and there's a reason why as well, because there was an impossibility theorem of instance encoding that was shared. So we generalize that problem into a metric DP setting, and we give an early mechanism for post hoc privacy for any informally trained network. You plug it into our mechanism, into our post hoc mechanism, and then you make it a privatized piece. So you can have like embeddings released with privacy guarantees, even if your embeddings were not designed with DP in place. You just do standard optimization. You have a non-private model. How do you make it private during the inference? So that's our post hoc privacy paper at NeurIPS. We'll talk about NeurIPS paper here as well. All right, thank you.
Any questions?
When it comes to data variation and differential privacy, isn't there like a fundamental conflict of having a very clear value, like assuming a data set D and one data point stands out in its variation, and assume it's a medical data set, wouldn't that inflict a privacy concern?
So that's exactly what's going to show up in the histogram. Yeah. It's going to say that specific record is maybe not easier to privatize because it's already a very skewed record. So it'll be, if you're going to push it to a lower epsilon, it's going to start trying to be farther from the lower epsilon, unless you really push it hard because you have a very good optimization scheme or guarantee. And it shows up that it is already a costly piece. So the utility function is at least measuring and telling you how difficult it is to privatize or how precious that record is from being very different than the rest of the thing. Secondly, we did a theoretical paper on that does a connection between social choice theory and like voting functions and differential privacy. So everyone talks about the utility privacy trade-off, right? But there's never been a trade-off that's been studied between the welfare of a collaborative mechanism, like a social choice mechanism, or like the influence of any given voter in a social choice mechanism. So we show a trade-off between privacy level epsilon and influence and welfare. But that's, again, like more like starting point work, although it's very theoretical. But the histogram is more practical because you have it computationally with you. Yeah, those are 2 things I can think of.
So another question, have you tried to train a generative model that generates these embeddings with differential privacy and compare that to your approach?
Oh, that's a nice application. We've not tried that. Do you see, are you seeing the benefit of being able to do that from being able, because it's going to be more distributed and client resource efficient generative model, or where do you think the benefit of generative model?
Possibly pre-training the model on public data, leveraging a lot of the things that you know of from the world, and then fine-tuning on the types of embeddings that you want on a population would help you in that sense.
Right, so I agree because of the benefit of public pre-training and private fine-tuning, which is, we've done that for a simpler problem, which is a predecessor to what I shared, which is if you're doing t-SNE or UMAP kind of a visualization, which is basically a query applied in the last layer of the network, and you just want to know how to do t-SNE or UMAP with DP. We've done that problem, and we use the private-public kind of a setup, and that's when we see like better gains in the utility for obvious reasons. But it's, yeah, I mean, I can see the value of what you're saying for more traditional ML like this.
Let's thank Praneeth. So that's the conclusion of the morning session. So now we break for lunch. I think we follow, I'm not sure who is supposed to, we follow Philip, whose hand's raised. We break for lunch, and then we meet back at 1:30.